Hey there, everybody. Welcome back. This is 14.3, Calculus 3. We're doing double integrals on polar coordinates. And let's just jump right into it. Some regions are just better using polar when we're dealing with circles, things like that, things that are round. So like an example, the semicircle, 0 is less than y, which is less than the square root of 25 minus x squared. And we're going from x equals -5 to 5, we could just do that as the radius is going from 0 to 5 and theta is going from 0 to pi. So integrals with x squared plus y squared often benefit from this change of coordinate system. This is x squared plus y squared equals 25, the example I gave. So we could have it, but it doesn't necessarily have to be a perfect circle. Anything with a outer line and an inner line like this, we're sweeping. It starts at an angle alpha, ends at an angle beta, and at each point it crosses a line. We might only have one radius, we might have two, so an inner and an outer radius or boundary. In polar coordinates, let's take a look at our integral. Our volume is the integral of the region. If we do f of r theta d alpha dA, well, what's dA and r and theta? Let's take a look at that. So we're evaluating at a certain radius and a certain theta. What does that look like? Let's draw a picture. So we've got an angle delta theta, and we got a radius r. So this little segment here is delta r. And RK star and theta K star are going to be smack dab in the center of that region. So this is our little region, and we're integrating with each little box. We want the center. You'll see that going this way or that way, each is 1/2 of delta RK, since this full distance right here is delta RK. So if we're doing it at this point, the inner radius is RK minus 1/2 delta RK, and the outer radius is RK plus 1/2 delta RK. We are looking at the area of this sector right here. So the area of a sector is 1/2 r squared theta, and we are effectively doing the whole sector for 1/2 the outer r squared theta minus the inner sector, this section right here. So we're going to deduct that one out. So our area looks like that. When we plug in what we have for outer radius and inner radius, you'll see that delta A actually simplifies into r times delta theta. Okay. So when we make this a dA, our dA, we put in dA, it's RK star delta RK delta theta K. That's what we were finding right here. What do we put in for delta A? And so now when we do the limit, this is just r dr d theta. So in polar coordinates, that's what you got to remember. R dr d theta, polar dA. It's important to remember. And it kind of flows off the tongue, RDR d theta. So many problems are often made simpler by this. We have to find the new limits of integration if we're in x squared and y squared though. So one way of doing it is we fix theta. We draw a radial line from the origin through our region at that fixed angle. And like we see in our picture here, it crosses the line at most twice. The region, not line, it crosses the region at most twice. And once we've done that, we'll label those R1 and R2, if there's two. And then we will sweep out the radial angle. So pictorially, we have our R and R1 and R2, and then we're integrating around the we're integrating around the angle. Okay, that's what's going on. And so we start at the lowest angle or the least angle and end at the greatest angle. You'll see some examples in the next video. Peace.